Hello guys, we want to start our ninth lecture. In this lecture, we want to talk about transform of derivatives, and then we want to use transform of derivatives to solve ordinary differential equations. So what's transform of derivatives? In fact, here we want to know that if, for example, I say I know Laplace transform of ft is equal to fs, f capital S, then I ask you what's Laplace transform of, for example, second derivative of ft. So based on transform of derivatives, we can find the answer. Transform of derivative says that if f dash f double dash up to n to the power of n minus 1 derivative of functions, so they are all continuous on the range of 0 to infinity, and they are all exponential order, and if nth derivative of function is piecewise continuous on the range of 0 to infinity, then Laplace transform of nth derivative of function is equal to s to the power of n f capital S minus s to the power of n minus 1 f at t equal to 0 minus s to the power of n minus 2 f prime at t equal to 0 and until f to the power of the n minus 1 derivative of function at t equal to 0. Now I just give you one simple example to see how we can just to check validity of this equation. So imagine this is example. Imagine I have a function like sine t. I know that derivative of function is cosine t. Second derivative of function it's minus sine t. Also, I know that f at t equal to 0 is sine 0, it's 0. F prime at t equal to 0 is cosine 0 is 1. If I want to find Laplace transform of f double prime, in fact, I want to find Laplace transform of f double prime is minus sine t. It's equal to minus, so Laplace transform of sine is 1 over s squared plus 1. Here I found Laplace transform of f double prime t using direct definition. Now I want to use transform of derivatives. So Laplace transform of f double prime t, it's equal to, based on definition, it's s to the power of 2. Laplace transform of is f capital S. So f capital S is what? F capital S is Laplace transform of f, is Laplace transform of sine t, which is 1 over s squared plus 1. In fact, I write it here. So fs, it's Laplace transform of ft. So it's equal to Laplace transform of sine t. And it's equal 1 over s squared plus 1. So it's s squared 1 over s squared plus 1 minus s to the power of n minus 1. So it's s to the power of 1 times f at t equal to 0. F at t equal to 0, we have it here, it's times 0. Minus s to the power of n minus 2 is s to the power of 0, which is equal to 1, times f prime at t equal to 0. F prime at t equal to 0 is cosine 0 is 1 times 1. So it's in fact equal to s squared over s squared plus 1 minus, so this term is 0 because 0 times s, and here we have s to the power of 0, 1. 1 times 1 is 1. So in fact is equal to minus 1 divided by s squared plus 1. So you can see that we ended up with the same result. As a result, we could check validity of this definition, derivative transform of derivatives. But as I already said, we want to use transform of derivatives for solving ordinary differential equations. So we can use Laplace transform for solving linear initial value ordinary differential equation, or ODE, in which the differential equation has a constant coefficient. So here at first we have to know what ODE is and what's the difference between ODE and PDE. So in ODE we have just one or more functions of only one independent variable and its derivatives. For example, let's say we have ft, so it's a function of t, and gt, and g is a function of t as well. So for example, second derivative of f plus derivative of g with respect to t equal to t. This guy is ordinary differential equation. But for PDE, or partial differential equation, so for example we have y is a function of t and x, and u is a function of t and x. So we have derivative of u with respect to x plus second derivative of, for example, it was the derivative of y with respect to s plus second derivative of u with respect to x and t is equal to, for example, t. So this guy, because we have two variables t and x, so we have PDE. So Laplace transform is just used for solving ODE. And what ODE? ODE with constant coefficient. In fact, if I want to write the general form of ordinary differential equation with the constant coefficient, which is initial value, so it's like this. In fact, we can use Laplace transform to solve equation like this. So an derivative of the nth derivative of y with respect to, for example, t, plus an minus 1 dn minus 1 over dtn minus 1 plus a0 times y, so it's equal to a function like gt. We can solve these ordinary differential equations. So an and bn, sorry, an, in general it's better to say ai is constant, an minus 1, and so on. And so here is initial value problem. As a result, we have to have values of function and its derivative at t equal to 0. So we assume that y at t equal to 0 is b1, y prime at t equal to 0 is equal to b2, and so on. The nth y at t equal to 0 is equal to bn. So in this case, bi is constant as well. So b1, b2, b3, and so on, they are all constant. So we can solve this equation using Laplace transform. Now we solve one example to see how it works. We want to use Laplace transform to solve this equation. So first we have to see if it's ordinary differential equation. Yes, it is, because we have only t as a variable. Then we have to see if it's with constant coefficient. Yes, coefficients constant. dy over dt, the coefficient is 1, y coefficient is 0.4, and we have 3 times e to the power of minus t. As a result, we can easily solve this problem using Laplace transform, and its initial value, because y at t equal to 0, it's given. So in order to use Laplace transform to solve this problem, we have to take Laplace transform of both sides of equation. So for the left hand side of equation, we have Laplace transform of dy over dt plus 0.4 Laplace transform of y, and then we have to take Laplace transform from left side of the equation, so 3 times Laplace transform of e to the power of minus t. So based on derivative of transform of derivatives, Laplace transform of dy over dt is equal to s y capital S. Y capital S is Laplace transform of y minus y at t equal to 0. It's Laplace transform of dy over dt plus 0.4 Laplace transform of y is y capital S. It's equal to 3 times Laplace transform of e to the power of minus t is 1 over s plus 1. As a result, so here I can just factor y capital S. So we have y capital S out, S plus 0.4 minus y at t equal to 0 is it's given here. Y at t equal to 0 is 5 minus 5. It's equal to 3 over s plus 1. As a result, y capital S it's equal to 3 over s plus 1 divided by s plus 0.4 plus 5. I just take 5 to the right hand side of the equation divided by s plus 0.4. Now in order to find yt, we have to find Laplace inverse of y capital S. So how we can find Laplace inverse of y capital S? For the second term is very easy, but for the first term, so we have a fraction, we have to use partial fraction to decompose it. So how we can decompose 3 over s plus 1 divided by 3 over s plus 1 times s plus 0.4. So if you look at the table that we had for partial fraction, so we have two terms here. We have a over s plus 1 plus b over s plus 0.4. So now I just add them together. So we have s plus 1 times s plus 0.4. A is capped times s plus 0.4 plus b times s plus 1. So we have two fractions, this fraction and this fraction, they are equal. Numerator is the same. As a result, denominator is the same. As a result, numerator should be the same. So 3 should be equal to a times s plus 0.4 plus b times s plus 1. So we can say we can plug s equal to minus 0.4, the second solution that we had. If I plug s equal to minus 0.4 in the equation, in the left hand side of the equation we have 3, in the right hand side minus 0.4 plus 0.4 is 0, so we have b times 0.6. As a result, b is equal to 5. If I plug s equal to minus 1, left hand side of equation is 3, right hand side of equation we have minus 1 plus 4 is minus 0.6. A. As a result, b is equal to a is equal to minus 5. So ys is equal to, so we found the partial fraction of 3 over s plus 1 times s plus 4 plus 0.4. So it's equal to a is minus 5 divided by s plus 1 plus b is 5 divided by s plus 0.4. So these two fractions are are partial fractions of the first function, the first fraction, but we already had 5 plus 0.4 as well, so I have to add it here. So it means that y is equal to minus 5 divided s plus 1 minus or plus 10 s plus 0.4. So now we can easily find Laplace transform of ys. So in fact, yt, which is Laplace inverse of y capital S, it's Laplace inverse of minus 5 over s plus 1 plus Laplace inverse of 10 over s plus 0.4. Laplace inverse of minus 5 over s plus 1 is minus 5 e to the power of minus t, plus Laplace transform of 10 over s plus 0.4 is 10 e to the power of minus 0.4 t. So we could find Laplace, we could find yt or solution of this problem.